Thanks for introducing me. I'm Sangpe from KAIST, and I will present our work on building cellular network state machine from the real traffic and how to exploit it to analyze the cellular network control plane. And this is a work done with my colleague Mincher and Professor Sue and my advisor Yongdae Kim. So let me start with some introduction to cellular control plane. So cellular network can be divided into two planes. User plane takes in charge of delivering data traffic, and the control plane manages the information flow and signaling between the elements in the network. So in the radio access network, user equipment communicate with the cell tower in Node B by radio resource control protocol, and especially mobility management entity, MME, manages the UE by NAS protocol. And it covers UE's authentication with HSS and set up the session by exchanging the signaling messages with the gateways. So once the control plane procedure is complete, the data service starts. Therefore, to enable cellular services, the control plane is crucial. And to provide high quality service, network operators strive to optimize their core network operations. However, analyzing the control plane is not simple, as the standard have over 5,000 pages, and it demands excessive engineering cost to analyze. And what it makes worse is that the standard leaves the freedom for operators to customize their operating logics, and it makes the diversity on the operation scenarios for the same control plane procedure. And recently, though, researchers exploit a state machine for analyzing the control plane. The state machine enables the systematic analysis with the help of model checking tools such as SPIN, and moreover, its representation makes it easy to exploit state information in the analysis. Therefore, it is employed to various applications such as formal analysis, finding security holes, and detecting design flaws in the standard. And in this work, as an application of state machine, we focus on the performance diagnosis of the control plane. And especially, unlike the previous work, we also want to construct the state machine automatically. And when it comes to the control plane diagnosis, a traditional way is latency analysis through the field test. First, a local tester measures the completion time of control plane procedure, then compares with operator's service level standard. And lastly, operators look closely at the signaling messages and standard to find the problem. In our work, we argue that these analyses have several limitations. And first, it ignores the various operational scenarios so that it easily leads to wrong analysis results. And second, it relies on local measurement, so it is hard to identify the ground truth for the measured latency. And lastly, it needs lots of effort for manual analysis in examining the lots of generated control plane messages. So along with the previous limitation, I want to stress that cellular network is still an interesting walled garden. And usually, the operators don't share their detailed network architecture and adopt different configurations based on their operating policies. And this nature makes differences in the network performance and diversity on the operation scenarios. So let's take a look at some example. So this animation shows control plane state machine among different carriers. And an interesting point is that there is one standard, but they look different. Then what can you do with this? Obviously, one operator implements a part or some part better than others. So by leveraging this nature, we may be able to figure out the bottlenecks or problems. So in other words, comparative analysis of state machine might be useful. And motivated by this, in this work, we come up with the idea of exploiting a state machine. So we set a goal, which is to conduct a fine-grained latency analysis with minimum manual effort while considering diverse operational scenarios. To achieve this goal, our strategy is to generate analyzable and comparable state machine automatically from the trace. Then to compare the state machine across global operators. And to do this comparative analysis, we first need to build a state machine. And for this, we take two approaches. And first, to define states, we bring state definition from the standard. This makes the resulting state machine comparable and analyzable because the standard state serves as anchoring point between different state machines, and the specification already described the status and operation of each state. And second, to connect state, we take trace-driven modeling rather than manual construction from the specification. And it also allows the state machine to adjust to real-world implementation logic. And here's an example. So first, when the UE communicate with the network, the baseband generates a log called diagnostic messages. And with this, we first parse the state-related messages and generate as a state. Then we define a transition as a sequence of messages between two states and store the timestamp information to compute the elapsed time. And by its design, each transition reflects a specific scenarios because different operation scenarios often, sometimes, or always involves different sequence of messages. And note that the standard only describes the transition with a short, high-level languages. All right, then how can you compare the state machines? And once we generate the state machine for each operators, a comparison is quite intuitive. As we focus on the latency analysis, we devise a pathwise comparison method. So in detail, as a first step, we extract the path, which is a sequence of transition from a source to sync state. Then we extract the shared path in other ISP state machine, which have the same transition sequence. And second, we compare the latency of each message interval in the shared path and find the long latency message intervals called LMI. And with this idea, we apply our analysis to 5 operators in 2 countries by physically visiting and driving there. And the dataset includes 400,000 of LT signaling messages and 20,000 of target procedures. We conducted various actions for collecting compressive signaling messages for the 3 main control procedures. And for example, the actions include turning on off the airplane mode and using a data or voice service in stationary and mobility environment. And first of all, I want to show how the state machine helps in analyzing the control plane. First, due to the transition design, it differentiates the operation scenarios for the same control procedures. So as the figure shows, the state machine handles 2 attached scenarios differently by defining different transition. And second, fine-grained comparative analysis provides the ground truth so that we can easily figure out the bottlenecks at interval A in US2 operator. Therefore, our design helps the analysis to demystify a hidden performance degradation point while considering operation scenarios. And with the pathwise comparison, we found 38 NMIs. So through the NMIs, we can get 3 implications. So first, each operator is optimized differently and not fully optimized for all the paths. And second, the NMI or the bottlenecks exist differently within the same control procedure according to the path. And third, NMI exists even in the path having lower total latency than that of other operators. And we also found differences in operating logic through the analysis on the shared and non-shared path. And for the details about the NMIs and in-depth study, and please refer to our paper. So not limited to find the NMI, our state machine representation helps to understand the problematic cases. One example is that the abnormal case consistently takes 5 or 10 seconds in US1 operator during a attached procedure. And this is represented as a path from registered init state to registered normal state in our state machine. And in addition, the state machine provides useful information such as previous state of the path and what messages the path has. So in this case, we can easily figure out that the attached procedure after the rejection in tracking area update procedure is working incorrectly. Therefore, this information helps to reduce the effort to analyze the abnormal cases. And our approach seems promising though. One of the biggest concerns is the completeness. While the trace-driven approach is effective in reflecting the operating logic, the completeness of model heavily depends on the collected trace. So one quick solution is to get larger data set through the crowdsourcing. And moreover, we are planning to build an active data collector. And with this, we can discover the missing state or missing transition at one operator from the existing trace, or even from the standard. And for example, if a path A exists in other state machine but not in US1 operator, we can send messages in path A and build the state machine more completely. And what can you do more with the state machine of comparison? And one interesting future work with the state machine is security analysis. First, by comparing the state machine, we can easily identify the possible security problems. And for example, a path heading toward service unavailable state or time-consuming state could be an effective attack vector. And moreover, a path which is not shared between multiple operators is a candidate attack vector for the operators that do not have the path as well. And to this end, we can conduct dynamic testing, which send invalid message actively to find security problems. And this approach is introduced by LTE first, and we believe that we can do more by exploiting the state machine information. And for example, with the path information, we can execute the dynamic testing at each path or testing with invalid transition. So in conclusion, we present a way to build a fine-grained state machine of cellular network via trace-driven modeling, thus requiring less effort for examining a standard. And with this, we highlight the comparative analysis, which exploit the walled garden nature. And as an initial stage, we conduct pathwise analysis over 5 operators and found 38 LMIs, which are deserved to further investigation. And we believe that we can devise more interesting comparative analysis with state machine, including security and operation logic errors. And these deserve further investigation too. So thank you for listening, and I would like to take any questions.